For any aircraft performance problem, we begin analysis by drawing a free body diagram. We begin the free body diagram by drawing a picture of the object being analyzed, in this case, the space shuttle in a glide. Next, we draw the axis system and the spacecraft's center of gravity. Because this is an aircraft performance problem, we gray out the drawing of the shuttle body and show only the center of gravity in black, indicating that we assume that the spacecraft is a point mass and that all forces act through the center of gravity. Now we draw the appropriate geometry of the problem. First, we show the shuttle's velocity vector as an arrow. Next, we show the horizon and the angle between the velocity vector and the horizon. We call the angle the flight path angle and give it the symbol gamma. Next, we show the forces on the spacecraft beginning with gravity perpendicular to the horizon. We now add the aerodynamic forces, drag parallel to the velocity vector, and lift perpendicular to it. We want to sum the forces parallel and perpendicular to the velocity vector, so we break up the weight into components in those directions. Since this is a stabilized, non-accelerating glide, the forces in each direction must be in balance. Therefore, we conclude that the component of weight parallel to the velocity vector must be exactly equal to and opposite in direction from the drag. Likewise, the component of weight perpendicular to the velocity vector must be exactly equal to and opposite in direction from the lift. Using a little high school geometry, we conclude that the aerodynamic forces triangle and the weight triangle must be similar triangles. There's another similar triangle in the problem. It's the triangle with the velocity vector as the hypotenuse and the horizontal and vertical distances traveled as the other two sides. We call the horizontal distance traveled the glide range and give it the symbol R. We call the vertical distance traveled the altitude or height lost and give it the symbol H. Using the principle of similar triangles again, we conclude that the ratio of glide range to altitude lost in a stabilized glide must be exactly equal to the lift to drag ratio of the spacecraft. We call this ratio the glide ratio.